Intro to Computer Vision. How many of you guys have like done some reading or like have tried to look into like what's inside a machine learning model before ever in your life? Okay, so like some of you have. So some of this might then be review, but some of it probably won't. So what I'm hoping to cover today is kind of a 10,000-foot view of machine learning. So sort of what are the kind of components? How did we get to where we are today? And I'm going to talk very briefly about how we kind of learn. So this concept of like how we actually optimize these models. I'm going to go into some detail on some of the lower level computational building blocks that you just stack all together to turn into a large neural network. I'll talk about a little bit about losses and training. We'll talk a tiny bit about parallel processing and introduce the concept of a tensor, which sounds fancy, but is literally just a matrix with more than 2 dimensions. We'll talk a bit about the concept of representation learning, so like what that means. And when we talk about things like embeddings, you know, what are we talking about? And then right towards the end, I'll introduce a bunch of different computer vision tasks and wax a little bit philosophical about why we have different machine learning architectures, and then go into some detail on specifically CNNs and transformers. Okay, so how do we get started? Back in 1958, Rosenblatt introduced the concept of what's called a perceptron. It was introduced in Psychological Review, so it was really coming from actually the neuroscience community. And the first perceptrons were doing this. They were essentially taking a picture of a letter, so an A in this case. They were taking values from the pictures, because remember that all images are just matrices of numbers. So here, this is a binary matrix. So they were taking values from sort of different parts of that matrix. They were combining them into features here. And then they were adding those together and trying to categorize whether or not this matrix contained a specific digit or a specific letter. And essentially, we've stacked up more different things. We've built more modern computational tools, things like GPUs that really make all of this possible to make much, much bigger than this. But this is still essentially what a lot of machine learning is today. It's just this idea that you have some input that's usually structured, something like a matrix or an image, and then you're going to learn how to represent the values in that matrix, map them through a bunch of different functions to get to something that is categorizable, that kind of matches some prediction you want to be able to make. So image classification then, like early image classification, was really, really rooted in this idea of feature engineering. So instead of trying to like learn everything end to end, for a really long time in computer vision, we thought about, okay, what are the things we need to know about an image? How do we craft the math that will tell us things about that? So here, okay, you have like a matrix of pixels, and now you're going to write some mathematical function that will try to find edges and tell you where all the edges are. You might write some other mathematical function that will represent something statistically about the texture of the image. And then you might have maybe a third mathematical function that tells you something about pooled values of color. These would be engineered features. And the reason we'd engineer those features is maybe I would say, okay, I know that clownfish have stripes, so there's going to be edges that go between orange and white. So I want to know, and they don't have a lot of texture. It's kind of smooth in between. So I want to know that there's like these 3 sort of white stripes and the colors are orange and white, and that will tell me it's a clownfish. And then maybe we would combine those into something fancier, like finding the segments of the fish. Okay, can we find the fins? Can we find the body? Can we find the eye? Can we find these, and then can we find maybe like those parts and categorize those? And then you would explicitly construct, you know, something that would tell you, okay, this is a clownfish. And early computer vision, it was all rules, right? You would just write mathematical functions, and you'd write rules around those mathematical functions that would tell you what is in an image. But this was really brittle. It didn't scale well. It was incredibly complicated to try to build a system where you could actually construct all those rules to be able to actually determine what was in an image. Because images themselves are quite complex. And you might build something that would work really well for a clownfish that looks like this, and then maybe you get a picture of a clownfish in different lighting conditions, and all the math would break, and you'd have to redo it. So then we started to learn to, instead of write rules, we would actually try to build something like a classifier that would take all of these engineered features and then optimize in a way to find the sort of mathematical function that would get you closest to being able to classify this fish. And so these are things like, if any of you ever heard of a support vector machine, basically like very simple classifiers that take in vectors of features and try to predict some output, usually something quite simple. But then, as we sort of developed more, mostly computational capability, larger data sets, kind of the underpinnings to be able to do this, we realized that you get much better results when you're predicting this stuff. If you don't input your human hubris on top of it and say, I know the best way to categorize a fish, and instead you let a model learn how to best categorize a fish itself. And so this mechanism of how do you actually build a system that can learn how to categorize is a lot of what modern machine learning is built on. And what makes this possible, what makes it possible to learn robust functions that are actually usable in the real world, is a combination of, the building blocks of like, how do you actually mathematically do this? How do you learn something? How do you optimize over these complex nonlinear functions? And then you need a shit ton of data. You need a lot of data, because these things, if they need to learn every possible way a clownfish is going to look, then you need to show it every possible way a clownfish is going to look. And then finally, we actually just needed the computational power to do it. And that's where GPUs come in. So GPUs are designed to be very good at doing very big multiplications in parallel. It's basically what they're designed to do. And they're originally designed for graphics rendering. They were really, the technology was really pushed by the graphics, like the video game and the entertainment industry, to be able to construct realistic representations of things like water or shiny surfaces. That takes a lot of parallel multiplication. And turns out that was exactly what we needed to be able to train neural networks. Because what we'll get into today is all a neural network is really is a lot of parallel multiplication. So then now, instead of having, something where there's all these sort of different specific structure we're building in, these days, maybe instead you'll just construct something like a neural net that will try to learn how you actually go from this input to maybe some intermediate features, from those features to some other intermediate features, and then maybe to an output. So this is potentially something like a multilayer perceptron. We introduced the perceptron before. It's really just like one linear, the perceptron is just like one linear function. So just ax plus b plus a non-linearity. Get into that a bit later too. And if you stack two of them, it's a multilayer perceptron. Mathematically, you can prove that a multilayer perceptron can approximate any function, absolutely anything, if you could learn it properly, and it would have to be big enough. A deep neural net is just you do that more times. You just do it a bunch more times, so you have a lot more of these kind of intermediate representations. You're learning a lot more weights, and that depth is actually really giving you a lot of the capacity to learn. And you can make deep nets approximate those same functions in a more computationally efficient way, because it turns out as you add more depth, you can kind of construct maybe more complex functions more efficiently. Okay, so this is what deep learning is. So we talked about how, okay, now you have like these layers and you're going to learn these parameters. So every one of these arrows is a function. It's a function you're going to learn. And these functions are parameterized by, different layers. So here, theta 1 is the parameters of function 1. And that function could be as simple as ax plus b. It really, in many cases, it is, right? It's just a very simple function, but you're learning what a and b are. And then you're mapping through one function to an intermediate representation, and then another function, and you're learning the values, the parameters in all of those functions through the network. And the way that it's learned is you construct a loss. So now you have your input, and you have what you really want the model to do, which is predict clownfish for this input. And then you construct what's called a loss, which is basically another mathematical metric that tells you how good you are at your prediction. How close are you to the true value that you want? And then that's about it. You do this a bunch of times, and eventually over time, you're just wiggling those parameters, right? You're wiggling them around and trying to get them to as close to as optimal as possible to be able to do what you're asking the model to do. And you're telling the model what you want it to do based on your data, which is those images and the labels. Of course, this is like the simple classification sense. We'll talk a little bit later about all the different ways that this can get more complicated if your label is not just something straightforward like a category, or it is instead something like a segmentation. But at its root, this is really all of deep learning. It's this idea that you're learning the parameters to a complex function based on data, and you're defining like a loss that is going to tell you how to learn that. Yeah, and so then if you're optimizing those parameters, essentially you're just trying to find the parameters that minimize that loss. And then your training data could be a bunch of different things, right? And the training data will really define what the optimal is. So the same task, categorizing species and images, with different training data. So maybe I have a bunch of images from my naturalist and you have a bunch of images from a camera trap. Even if our goal is the same, which is like, okay, so tell me if it's a grizzly bear or not in an image, the optimal value of the model will be different based on the data that we have, right? So like the same model, even if we have the same task, might be completely different if we train it with different data. So how do we actually train it? What's the way that you do that optimization? So the term we use is called gradient descent. So essentially, you define, okay, we want to find this theta, we want to find the values of these parameters that minimizes our loss over all of our data points, right? Pretty straightforward. So sometimes we'll call, some textbooks and stuff will call this J, which is essentially just like a representation of that sort of summed loss over all of your different data. So now, if you imagine that J is kind of a simple thing, so maybe only in a couple dimensions, this is what we would maybe call the loss landscape. Essentially, like if you took every possible combination of your parameters, so now if this is just, we only have sort of two parameters in the model, theta 1 and theta 2, and you take every possible combination of what those values could be, and you calculate what the loss is over your data, that will build your loss landscape, which is essentially just like how good is this combination of parameters for your loss. And so this loss landscape you can see is what we call non-convex. Most of these losses are not convex. Convex means there is one minimum, and no matter where you started, if you like think of this as like something where you could drop a pinball and you wait for the pinball to roll to the bottom. If you have a convex function, it's well behaved. The pinball is always going to find the bottom, and it's going to be the true bottom. In this case, you can see that there's a couple like places where a pinball might roll, or you can end up somewhere over here where your pinball would kind of get stuck and wouldn't roll anywhere. And so this is where we'd actually like to go, but now we actually sort of have to figure out, given some starting point, some initialization of those parameters, how do you learn how to update them so that you're moving towards that minimum? You're moving towards the thing that's going to be optimal, or at least hopefully close to optimal. And so what we actually do in order to do this is we do something called gradient descent. And for simplicity, we're just going to talk about gradient descent over sort of all the data. So say you initialize your model and it turns out your initialization wasn't very good, so you end up like way at the top of this loss mountain. So now, essentially, the best way to update your parameters is if you could take the derivative of that lost surface, you can figure out which direction to move in that will take you maximally downhill. And you can imagine you always want to go downhill because you want to get as close to as possible as to the very bottom, right? So now we started our initialization, we calculate the loss over all of our data, and then we calculate the gradient. And we're not going to get into the details explicitly of how we actually do that. It depends on different things, but what you can do, kind of amazing with PyTorch, is use something that's called AutoGrad, built in implicitly. And AutoGrad will calculate a gradient for anything. It is a really nice approximation function for gradients. And so we don't have to worry too much about actually manually deriving the gradients for different types of functions or layers. They actually just get approximated really accurately directly through PyTorch for us. It's one of the reasons that it's so much easier for all of us to do machine learning today, because we are not actually writing all of that math from scratch. Okay, so we use AutoGrad, we calculate the gradient, and it tells us to move in this direction. Cool. So now this is where the concept of a step size comes in. So now you, when you're building your deep learning model and you're defining your training, you're going to say, how far am I going to step every time I calculate that gradient? How far am I going to move? And you can imagine that actually could really affect things a lot, right? Because if you step super far based on just a single sort of data point, you might end up going somewhere way off where you didn't expect. So often this is where it kind of gets into black magic. Often we'll do what's called like a learning rate sweep. And learning rate is another term that people use for that step size. Basically, how much are you going to wiggle those parameters every time you take an optimization step? And so often we'll do what we call sort of a hyperparameter sweep. Those hyperparameters are things that we define for the model when we come in. And so a hyperparameter, one of them is learning rate. And so if you're going to take your architecture and your data, you might actually try a few different learning rates to figure out which one gets you the best optimal. Because that actually is something that you have to decide and it will change. And then if you want to get really fancy, there's now a bunch of built-in like learning rate schedulers that will vary your learning rate over time and do all this cool stuff. But from a simplicity perspective, you just pick a learning rate and then you try to find that optimal. Okay, so now we've moved in that direction. Calculate the gradient again, calculate again, move again. And you do this, and hopefully eventually you get to that, that minimum. Now, we almost never actually do what's called gradient descent, because that would imply that you're going to calculate the loss for every single data point in your data set, every single step. And it turns out that that's inefficient and expensive. So what we actually do is something called stochastic gradient descent. And stochastic gradient descent is basically just you take a subset of your data, you calculate the gradient, you assume it's a reasonable approximation of the total gradient, and you use that for each step. And then each step you take some new subset of the data. And in a nice way, actually, by taking these subsets, or what we call batches, I'll talk a little bit about that later, sometimes you actually build in a little bit of regularization, or like a little bit of randomness into the system. That means that you can sometimes find a more accurate minimum than actually if you had calculated it completely every single time. Cool. Yeah. So each arrow is like another, like I could have stuck an X between each arrow, I guess. So the X here was representing the starting point of the parameters. So now for each of these steps, you would use a different batch. So the images themselves, like you would use some subset of your data. It could be half, it could be a third, it could be 10 images for each batch, it could be 200. And you'd calculate what direction you should move in based on that batch for each step. Yeah. Yeah, so actually, yeah, that's totally true. If you wanted to be really like literal about it, essentially every subset would end up having its own topography. And what we're assuming, which tends to be a reasonable assumption, is that if your batch is big enough, the topography will be close enough to this topography that you'll get a reasonable approximation of the right direction to go in for the whole data set. That's a great question. Yeah. So hyperparameters are ones that you define at the beginning. Regular parameters are what we're learning. So these are the regular parameters in the model. So when we talk about model parameters, those are things that the model's going to learn with this optimization. A hyperparameter, I don't know why we call them hyperparameters, but a hyperparameter is something that we define in a configuration file at the beginning. So like the learning rate is not something that most models learn. It's just defined. Yeah. Batch size is a hyperparameter. Another hyperparameter is something like the image size that you're going to use, the input size to the model. There's a lot of different things. Yeah. Thank you. Thank you, Björn. Yeah, I'll try to reformulate the question so that the recording is more accessible. Cool. Okay, so now if we think about computation in a neural net, there's a lot of stuff that goes on here, but essentially all neural nets are taking you from what we call an input representation, like any sort of computational building block within a neural net is going to take you from some input representation. So we can almost always assume that these are vectors. You can make any image a vector by just flattening it out, and that's often what we do. So assume that these are vectors, and now you're going to map from some input representation to what we call an output representation. And that representation mapping is going to be some form of function. And so now I'm going to introduce the most basic form of a computational building block or a function that we might learn. And that's what we call a linear layer. And this looks a little fancy here. This is literally just y equals ax plus b. That's all it is, right? So here, our input representation is a vector. So we have each element of the vector is some value. These are all just numbers. And then the output is going to be some vector. Maybe in this case, it's the same size. And the actual thing that we're learning is what we call weights. And so now you can imagine that if you would have this same mapping from your X input to every single one of these outputs, where you're going to learn a weight that will take you from all of this input to this output for every single one, right? So let me try and make that more clear. Basically, if we're calculating Z sub j, so this specific one, it's going to be the sum of weight of ij times x sub I for all I. So you're basically summing up multiplications. It's a sum of multiplications. It's essentially the same as like any sort of linear function, right? It's just multiplying values by other values. And then sometimes we'll also have a bias, what we call a bias term that's just added on. So it's not part of that multiplication. So that's the mx plus b or ax plus b. So does someone have a whiteboard marker? Do you have your whiteboard marker? You have one? No, but that is, I'll pull this over here so it's visible. Okay, so when I start thinking about stuff like this, sometimes it helps me to think of it as vector multiplication. So essentially what you have here is you have your input, which is like a vector, right? And so it has a bunch of values like this. And now this is x. And now you have maybe some weight vector. It should be the same number, 1, 2, 3, 4, 5, 6. This is w, right? So what we're gonna do, wait, am I doing these the right direction? Okay, what I want it to be is wx, so maybe I need to flip them, but equals z. So you basically are multiplying two vectors together to get each sort of individual output. I'm not doing this the right way. Yeah, that will help me. Okay, here we go. I'm trying to make this more clear and I'm worried that I'm making it less clear, but you guys tell me. So you can think of this like essentially instead of writing this as a bunch of diagonal lines like this, I'm trying to point out that every single one of these weights is also a vector, right? And so this would be w sub I, right? Because it's the weights that correspond to, or j, the weights that correspond to z sub j, right? So every single one of the outputs of z is going to have a corresponding weight vector that you learn, right? So then if you wanted to do it all together, instead of having w sub j times x, now instead of having a vector times a vector, you can just expand this and have it be a matrix times a vector, right? Because now each one of these rows will be like, this is your big W. Each one of these rows will correspond to one of the J's. And so then if you have like big matrix W times X, that will equal Z. Because it will now give you, you can do this multiplication essentially in parallel for each of them. And then you get out the Z vector instead of just a single element. And this is why, because we mostly use linear layers inside these things, so much of machine learning is just multiplying matrices. Because then, we'll talk about this a little bit more later, but now what if instead of just one X, which is one data point, you had a batch of them? Well, it turns out you can just put those all in parallel as well. And now you're doing matrix times matrix, and now you get the output of Z for a whole batch of input images. If you guys have not done linear algebra in a while, that's totally fine. Just like essentially all you're doing is multiplications and addition is all I'm trying to say. Yeah. Mm-hmm. For ZJ. So for ZJ, for a linear layer, you would have a weight for every single input dimension of X. Yeah. And then you'd have that for every single Z. Cool. And then sometimes you have, like I said, this. Oh yeah, go ahead, Guy. Yeah. So these weights are those. All of the weights in the whole model will make up the parameters of the model. The weights are what's going to be learned. So you're trying to figure out which weights will optimize your loss. So if you define like a bunch of different linear layers, now you have a lot of different weights, right? And so you're going to calculate that gradient based on the current set of all the weights and a set of data, and then using some defined loss. And I'll talk a little bit about different structures of loss later. But so these weights, it's essentially like, this is like, when you're doing those, when you're calculating the loss, you freeze all the weights. You say like, okay, this is the set of weights we're considering right now. Now we calculate the loss for that set of weights for my set of data. And then we figure out which direction to change the weights, how you move in that gradient. And so when you're taking one of those gradient steps, you're changing these weights a little bit. And how much you change them is that learning rate. Yeah. It's not comparing. So the question is like, now you have like each one of these outputs has its own set of weights. So those weights are actually just defining what that output representation is going to be. So you're not doing anything about them now. So now like you're using whatever your current weights are to map from one vector to another vector. And then you'll probably do it again, and you'll do it again, and you'll do it again, and eventually you'll get to something that you use to actually predict a class, for example. But at this point, like this is just defining the function that maps us from the input to the output for any given layer. Yeah. Yeah. Yes. So the question is basically in the input representation, if this is the first layer in the network, then we would assume that those inputs are just representing pixels, right? So each of these xi's would be a given pixel. And then the question is now in the output representation, that relationship between individual pixels is broken. And the answer is yes. And we'll talk a little bit later about what we call like receptive fields, which essentially like is mapping back through the network to try to figure out which input pixels were able to contribute to the value in some point in your output. But if you assume a fully connected linear layer like this, where every single one has a weight to every single output, then at that point, all the pixels would contribute to everything. So basically, as soon as you get to this next representation, you've abstracted away the original pixels. Yes, so that's also true. So right now we have X and Z being the same size, but you could define Z sub J, you could have this be only 3 of these, right? And that would maybe, now you're getting maybe a smaller information capacity as like a bottleneck or something. And a lot of those choices about like how big the different layers are and like what sort of parameters you want to use, like how much combination, all this stuff, that's what defines the architecture. Yeah, cool. Okay. So then this bias term essentially is just like in that mx plus b. So you can, any linear function can have like this bias term, which is just like shifting everything by some scalar value. The way we actually do that is you just append a 1 to the end of your input representation, and then you learn a weight from that as well, and that gives you that bias term. And so this is now essentially just showing you like a linear equation. Y equals mx plus b, or wx plus b. Okay, so This is kind of what I was showing before, but you can, instead of writing this in that summation form, you can write it as vector multiplication. And then now the parameters of your model is basically big W and B, which is just all the weights and all the biases. And those parameters are the things that get learned. Do you want me to share the slide? Would that be helpful to share the slides? Yeah, I can do that. They're Keynote, but I can, so that'll be tricky for people who are not Mac users. Yeah. Maybe someone could convert them to a PDF if there's people who have Windows who want to use them. I would do it, but I don't want to spend a bunch of time doing it. Cool. So now we defined this linear layer, which takes you from some input with weights, and now you get Z. So in this simple version, maybe Z is just a single value. And so then the other little bit of magic that makes a deep neural net or a neural net is the concept of now what we call a pointwise nonlinearity. So if you just stock a bunch of linear functions next to each other, if you do a bunch of different linear computations, the output will also be a linear computation. And so the way that you kind of increase this capacity in the model, and you make it able to do something that's beyond just a simple linear computation, is by adding these nonlinearities. And so what is a nonlinearity? Sounds fancy, but they can be very simple. So one example of a nonlinearity is just this. So you basically just set it to whatever, you set it to 1 if Z is bigger than 0 or 0 otherwise. That's an example of a nonlinearity, right? And so basically what this function would do, this is what we call maybe like a gating function. The simplest possible nonlinearity, you just have some threshold and it essentially sets every negative value of Z to 0 and then lets all the positive values maybe pass through. This is not actually the nonlinearity we actually use, but this was the one that was used in that original perceptron that was defined back in the 50s. So if you want to do linear classification with a perceptron, so now you have this, let's assume a really simple model, right? So we don't have an image here, we literally just have x1 and x2, so like 2 numbers going in. We learn weight 1 and weight 2, and then, so that gives us Z, right? So now you're gonna basically say like x1 times weight 1 plus x2 times weight 2 equals Z. And then we pass through some nonlinearity, which is that like if it's positive, set it to the value. If it's 1, if it's negative, set it to 0, and that gives us Y. So what I'm going to prove to you is that if you have a linear function plus a nonlinearity, you can build a linear classifier. So if you essentially define for some set of weights, like if you have your set of weights and now you have like x2 and x1, that will essentially define a ramp in 2 dimensions, right? So now there's going to be some values that are high and some values that are low because it's linear. Now, if you add that nonlinearity to it, essentially what you're doing is you're like cutting through that ramp at some point, and you're setting everything above that to 1 and everything below that to 0. So now you can imagine this now becomes a classifier. This is something that will tell you for some combination of x1 and x2, the value is positive, and for some combination of x1 and x2, the value is negative. And so a single layer neural net can perform linear classification. Okay, so how do we think about how well a neural network fits the data? So if this is your data, again, where it's super simple in 2D. So these are the values of x1 and x2. And then the points here on this space, that's what we're going to call our training data set, where those are the ground truth values. So like here, if I got, if x1 was 1 and x2 was 1, then the ground truth would be 1, right? So you have some, like the numbers on top of there are just defining the labels for the classifier that we want to learn. And now we want to find the weights and biases that will minimize our loss so that we can classify this data set correctly. So maybe your initial point, your initial sort of classifier draws that line that we just defined. And look, so here, maybe you're classifying some of these correctly, but a lot of them incorrectly, right? So this would be, the loss would be high, you're having 7 misclassifications, and then you would take one of those learning steps and try to update the model to have a better fit for that classifier. So now maybe it gets shifted a little bit, those weights get changed, the classifier gets shifted, now it's maybe doing a little bit better, now you only have 4 misclassifications, and then with your next learning rate step, you actually are able to fit the data set perfectly. So this is, of course, like a very simple version of the problem because we're only dealing with 2 input numbers, but you can kind of start to see how you're like learning a classifier over time in that process of learning the correct or the optimal weights that will actually predict the way you want it to predict on your data. So what do we actually use for nonlinearity? Yeah, go ahead. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. So this, yeah, so this has to do with, this is a perceptron, and that perceptron, the nonlinearity literally maps things to 1 or 0, right? Like that, it just takes everything that's positive and makes it a 1, and everything that's negative and makes it a 0. And so that nonlinearity doesn't actually give you a lot of information. And actually one of the things that's tricky about it is like, you don't have a sense of how close you are to the boundary based on that nonlinearity. So you don't have as much signal for training. So the way that your model is giving you like a score, it just depends on how you define your loss and how you define the outputs of your model. And so instead of having, actually, I'm going to put a hold in this question about scores until I talk about cross entropy loss in a little bit. But essentially, the reason that this model is giving you 1s and 0s is by construction. The nonlinearity that we used literally can only spit out values of 1 or 0. It can't spit out anything else. Yeah. So this kind of gets close to that. Actually, what we often use in practice, though there's a lot of fancy innovations on top of this that people sometimes use instead, are these rectified linear units or ReLUs, which is, again, the nonlinearities within the model are really simple. Like these models are just linear multiplication, incredibly simple in nonlinearity. And what this is it, if it's negative, it sets it to 0. And if it's positive, it's linear. So it's literally just taking the value and sending it through if it's positive. Super, super simple when it actually comes down to what the math is doing inside the models. Okay, so then we can start stacking layers, right? So you have some input representation. You run through your model, which has all of your weights and biases. Now this is our first layer of the model. We've run it through. We've got some output representation. We map through a nonlinearity. And now we have what we call sort of this intermediate representation. And then you do it again, right? So now you'll build a different set of weights that you're going to run the model through. And this is our second layer. And now you're going to do that exact same thing again. And then maybe this gives us our output representation that then we'll use to try to classify or do something else, like regress some value. So essentially, we learned now a lot about the details of the simplest building block. And now you can take those building blocks and you can modularize them and you can just stack them in sort of infinite different ways to build neural networks. And so here, you know, if you consider this first layer to be a function g, then g would h, which is the output, or sorry, g is the nonlinearity. So h was that intermediate output, is g, which is that nonlinearity, pointwise nonlinearity applied to, you know, mx plus b, w1x plus b1. And then y is going to be the same thing again, but now you're, instead of using x, you're using h. So it's basically just stacking simple functions on top of each other. And then your parameters, theta, that are the parameters we're going to learn using our optimization, are all of those different weight values for all the different layers in the model. So now, if we want to do nonlinear classification, imagine you had 2 layers, right? So this is really just for intuition building, but all we could classify before with the perceptron was a linear classification. But now, what if we had something that was nonlinear, where we needed to classify like this curved bit as ones? So even with just 2 layers, you have one ramp, right? Now, essentially, you're intersecting that ramp with another ramp because you have 2 different linear layers. And now, if you slice through that, you can get something that's nonlinear, right? And so this is kind of just demonstrating how by stacking layers, we can increase the complexity of the classifications that we can actually do. They no longer have to be linear classifications. And in fact, with many layers, you can build quite complex classifiers. Okay. Everyone want to stand up and stretch for a sec? Okay, stand up and stretch. You guys doing okay? Is this interesting and good? We're good? Okay. I hope it's not horribly boring. I don't know, man. Okay. Training loss. Let's learn about cross entropy. So we said that deep networks are basically stacking linear layers and nonlinearities, and we stack a bunch of them. And at the very end, you're gonna classify, what something is. Okay, so how do we actually build that last classifier layer? How do you get to the point where you're actually trying to classify something? So maybe what you can do, and what we often do with a classification network, is you have that final layer be the size, so it's a vector, right? It's the size of the number of categories you care about. So if all you care about is shark and not shark, then your classifier layer would be 2. It would only have 2 values, shark and not shark. If you care about dolphin, cat, grizzly bear, angelfish, chameleon, clownfish, whatever, then you'll have maybe a much longer output vector that's going to have a single element that represents every single one of those categories. So essentially now what you're trying to figure out how to do is, how do I get my model to output something where clownfish is the biggest value, right? And that's where the scores come in. The size of the value of the number in that output would be often is represented as a score. Yeah, so essentially you've run that through all of your different layers. And then basically right now what I'm trying to talk through is how we construct a loss function that will get it so that if you take an argmax, if you take the maximum of your output vector where you have one value for every single category, it will give you the right answer. Yeah, so the maximum is basically like, I want it to tell me something like, this here is how confident I am, like the value. So here the like higher, darker is higher, right? So the value for the true category, you want to be the highest value in that output prediction. Yeah. So if the ground truth label is clownfish, and the way we're constructing our classification is we just take the maximum value at the end, then our loss is essentially the error between the true value, the true ground truth label, which is clownfish, and this. But how do we define this loss so that you can actually demonstrate that we want the true ground truth label to be what you want to match? So you want the loss to be small if the ground truth label is correct, and you want it to be large if the ground truth label is not correct. And so what we actually do is we turn our classification labels, which are just like words, into what people will call a one-hot encoding, which sounds fancy, and I don't really know why they don't just say, make it a 1 for the thing you want and a 0 everything else. But that's what it actually means. One-hot encoding means the ground truth label is going to be 1 for the thing you care about. So in this case, the true value is grizzly bear, and 0 for everything else. So now you have a vector that's the same length as your predicted output of your model. So now you have 2 vectors. And the values of the ground truth vector are just zeros everywhere except for one place where it's a 1. And that demonstrates that this is what you want it to be good at. And then essentially we construct this loss. This is called cross entropy loss, which is essentially something like, we want the probability of the observed data under the model to be as close as possible to correct. So if we take our prediction, and here, maybe this is we've taken like a log so that it's matching into that that kind of cross entropy probability as close as possible. So now what you have is you have values for all of these different categories, and they'll all sum to 1 because we'll take what's called a soft max over the last output prediction, which basically forces all the values to sum to 1 and maintain their relative sort of volumes of score. So now you have a bunch of stuff that sums to 1, again, because we want it to be kind of like a probability, though I think it's really important to state that none of these are true probabilities, right? These machine learning models are approximating probabilities, but they're not true probabilities, and it's not anything like a real probability, but people will sometimes call it that. I like to call it a score because it makes it clear that it's not a probability, in fact. Okay, so now you have your prediction, you have your ground truth, which is just 1 at clownfish and 0 everywhere else. And then your score is essentially how much better you could have done for that correct value. So you're essentially saying my loss is if I predict clownfish, you know, with this like log probability of something that's small, or if I predict it with after you've taken that softmax, if I predict it with like 0.3, and that's the biggest one, but that's the one I actually care about, then, and this value is 1, then essentially what you want, like your loss is going to be how much better you could have done if you predicted the correct thing correctly. So if my prediction is grizzly bear and I have a much, much higher confidence that it's grizzly bear, the value of my output is much bigger for grizzly bear, then the loss will be smaller, right? Yeah. Mm-hmm. Yeah. Yeah. So basically for any given image, you're basically only calculating loss relative to the thing you care about, because everything else is 0, right? And then, you know, say, okay, I actually predicted iguana, like was the highest valued thing in my prediction. The true thing was chameleon. Well, I don't penalize myself for iguana. I really just look at how much worse, like how much better I could have been if I had predicted more for chameleon. Because you can't predict, like because you force them to kind of sum to 1, essentially, like you can't predict 2 things super high. So you're like kind of forcing the model to make a decision, and then you're rewarding it or penalizing it based on how good that decision was. Cool. So that's what's called cross entropy loss. There's entire areas of research in machine learning around constructing these loss functions, improving on loss functions, adding different terms to the loss functions. We'll talk a little bit about some of the different tricks that you might want to add in next week to improve your basic models. Things like maybe adjusting the weights in your loss function if you have really imbalanced data, to try to force it, to penalize it more if it makes mistakes on rare stuff. There's ways to kind of adjust your loss to try to convince or train the model to do what you want it to do. And a loss is really, by definition, it's something that you're constructing, and it's really defining a lot of like a hypothesis for you, like what you want the model to predict well. But cross entropy losses underpins a lot of, anytime you have a category, we often use cross entropy loss. If you're interested in predicting values, you might instead use something like a regression loss, which might just be something as simple as mean squared error. So there's lots of different types of loss for lots of different types of tasks in computer vision. But I think this classification loss is a nice illustrative example, and one that many of you will probably encounter. All right, so now we have some loss. Again, we're just like trying to learn all of these weights that map to all these different functions throughout the model that give us the best possible score for our loss. So now, you know, you're moving through and you put in these different things and you're calculating these losses for all these different images. Based on that loss function we define, you add up all the losses, and then you're trying to minimize that to find the best parameters. Cool. So I'm not actually going to talk through backpropagation because I think it's a little bit overkill for this class. But backpropagation is a fancy mathematical trick that is what actually helps us calculate the gradient for these really complicated nonlinear functions. And if you're interested in learning more about that, like underpinning of like how you actually figure out which direction to move your weights in and how you do that weight update, like the math underlying it, let me know. I can send you some slides. I'm also happy to point you to some resources on it, but it seems a little overkill for this. Essentially, backpropagation is the mechanism we use to figure out how to make that update to the parameters at each step. Cool. So parallel processing, this is pretty quick. But essentially, we said, okay, you can calculate you run the model through all of these functions. You get a loss. Now you can do that because the losses are additive, you can do it for a bunch of different images all at the same time, assuming the same fixed set of weights. So now you're doing this in parallel. All of those matrices can just be reused for every single item in your batch. You sum up all of the losses and calculate your loss, and then you calculate the gradient, which is how you want to update the weights within the model for all of them sort of combined for every batch. And this is really nice because it turns out parallelization is something those GPUs are designed to do really efficiently. So more parallelization is more computational efficiency, which means you can train faster. So as long as you can fit your batch size in memory, the largest batch size possible tends to be the most computationally efficient. And also because the larger set of images you're considering when you're calculating the gradient means you're getting a better approximation of that true loss landscape. That also helps you train faster because you might not be so stochastic in terms of your direction of movement. So here, you basically are taking the weights for each image and you kind of stack them up. So now you have all of your different images and you have all of your different features for all your different images. And then you have these big matrices you're building and just doing matrix multiplication. Okay, so I'm gonna introduce briefly this context of what we call representation learning. This is terminology that often comes up when people talk about modern machine learning. So now we're zooming out from the brass tacks, the underpinnings, the little modular blocks and mechanisms, and zooming out a little bit more to some of the philosophy behind how we think about representations and those embeddings and the layers within a model. So at their core, deep networks are data transformers. They're a way to transform data from one representation into another representation. And essentially, you can think of them as transforming data points, so images layer by layer. So you're transforming them through layer 1, again through layer 2, again through layer 3. And every single one of those layers can then thus be considered a different representation of the data, right? Every single one of those kind of intermediate vectors or matrices are a representation of the input data. And we call those representations or embeddings. So a lot of times people will talk about oh, well, use the embeddings from this model. What they mean is essentially run your data through a model as a data transformation to get some representation that might be useful. So when people spend a ton of time and money to train these foundation models on all of the images on the internet, what they build are basically data transformers that are useful. They'll transform any image into something that is kind of closer to ready to be categorized. It's a more information-rich representation and maybe quite computationally efficient. Because an image, if you can imagine, is hundreds by hundreds of pixels. This is a really large representation. And sometimes those embeddings that we take are a vector of only 1,000 points, right? So it's a much, much smaller information space. So if you think of a human brain, we also do this, right? I take what I'm seeing in front of me, I pass it through all of these kind of neurons through my brain, and eventually I get to something that represents categories or concepts or semantic meaning. And neural nets are kind of doing the same thing. So this is a figure from a paper back in 2014. But here the idea is all right, so you have this image of a fox. So when we think, the intuition we build about what these neural networks are learning is often that these really initial layers, the representations, what you're learning in those really initial layers, often tend to be really basic concepts. So here they might be things like directionality of edges. And then maybe the next layer gives you something like more complex types of structures, like you're looking for spirals or triangles or something, right? But these are still these really abstract kind of low level features or low level concepts. And then as you move through the layers, essentially what happens is the representations become more and more abstract. So you might actually start getting representations at later layers of the network that are doing things like representing eyes. You'll see that, right? We can talk a little bit later about visualizing what the networks are looking at, and you can actually show that you really will have some certain features in a network that might focus specifically on something like an eye, or focus on a nose. And so you kind of get these features in the network that tend to learn to kind of capture some of those things that we might have initially defined ourselves, right? What does an eye look like? How do we write the math for finding eyes so that we can write some rules about how many eyes and where they need to be placed to be able to categorize a species? And if you actually take, like this is a data set of images of different categories, so things like structures, hunting dogs, birds, whatever. If you take early representations in a machine learning model, so if you use the intermediate representations that are early in a model from like the first or second layers, what we see is if you plot those representations in like 2D, so like you take PCA or something, they're all over the place. All the different categories are really mixed together. Those representations aren't very separated. They're not very semantically meaningful. And then as we move to the later layers of the network, what we really see is that you actually start to get more separability in that embedding space or in that representation space. So as you move to the later layers of the network, they become more semantically meaningful. They're maybe more rich in terms of like the categorizations we might care about. We're just understanding things like similarity. So when people talk about representation learning and they talk about embeddings, they're often talking about using a machine learning model as just a data transformer in some way, and then taking a representation for your data and using it in some other way. So one way you might think about reuse, say we have that this initial model, it has it's been trained to do this animal classification. We have all of these weights, all of these biases, whatever that have been learned. They're optimal for this task. When we talk about reuse, some intuition that we might have is that a lot of parts of this model are not specific to animals, right? Like there's nothing about edges that are specific to animals. And so actually this might be a pretty good starting point and maybe a more efficient starting point if I wanted to now move from animal classification to something like satellite image building classification, right? Because a lot of what this model's learned is like how to deal with images. What types of things in matrices that represent images are important. And so when we talk about reuse, or what sometimes is called like transfer learning, or sometimes like few shot learning, essentially it means that instead of using this model and all of these weights to classify animals, we're going to take a lot of it, maybe up through layer 4 or something, but maybe not the whole model. And we'll just take all those weights and we'll plug them right in. And then maybe we'll add just this very end, this new classification head. So a new layer right at the end that just does the new classification task we care about. We'll define our loss function that we care about for this new task, which is like, is this building damaged or not, I think. And there, you're essentially reusing these pre-trained model weights. And that's useful. And often it can really help you if you don't have a lot of data, because you don't need to learn everything about edges and color. You can just start by trying to learn how to take all the building blocks about edges and color that other models have learned and then use them for a new task. So maybe useful. Okay, let's take a break. Yep. So maybe come back in 5 minutes. Okay, cool. So we talked a lot so far about like very, very simple stuff, like 2-digit classification. And we talked about, simple classification, things like multi-class species classification. But there are a lot of different things that people use computer vision models to do. And even like what I'm going to introduce right now is really just scratching the surface. It's kind of amazing. Like if you can imagine it might be something you might want to be able to predict, there's usually a way to construct a machine learning model to predict it. And I'm not even scratching the surface of things like predictions on graphs, like graph neural networks, or predictions on things like text. Like we're not talking about NLP right now. We're really just talking about vision. But so the simplest vision tasks are often things like classification. So if you had this image, maybe the classification task would be like, what room in the house is it? What's the answer? What room in the house is this? Yay. Kitchen. So yeah, so maybe that's it, right? You just want a model that will tell you what room in the house something is. But you can also get a little bit more fancy. So classification is just something like, okay, tell me one answer. But you can also do something called detection. And what detection does is it doesn't just tell you categories, it also tells you where in the image those categories are, right? And so here what we have is we have boxes around a bunch of different things like bowls and chairs and microwaves. And so when you're actually training detection models, and some of you will be, and so if we want to get into it a little bit more later, now you're not just using that cross entropy loss to predict a category, you're actually using regression to predict the points of the corners of the bounding box, right? So you're trying to regress the accurate values of where those box corners should be. And then you're trying to categorize what is inside the box. So you have this kind of combo loss that's basically trying to find the locations of those box corners and predict the category inside of them. So you have both a box loss and a categorization loss. So this is essentially just increasing the complexity of the thing you have to learn. And it also means that if you want to train something to do detection, you need to have labels for detection, right? So you need to actually show the model what you want it to do. It means you have to have images that have boxes with category labels. Moving beyond detection, where you're just regressing the corners of things, you can also do what's called segmentation. And there are two kinds of segmentation. They're what's called semantic segmentation. Semantic segmentation means every single category, every single pixel gets a category. So this is semantic segmentation. So every single pixel in the image, actually, no, this looks like instant segmentation. Oh, anyway, okay. Every single pixel gets a category. If this was semantic segmentation, then I would suggest that actually the two chairs should have been the same color, right? Because you're saying all the pixels that are chair get one color. If you're trying to find all the wetlands, you would have one color. So every single pixel is getting a category loss. And so now that you're doing that same cross entropy loss, but now you're doing one for every single pixel in the image. Same type of categorization, but now the structure of the output is different. Now you can get a little fancier than semantic segmentation, and you can do something that's called instance segmentation. And when you're doing instance segmentation, now instead of just saying every single pixel is a category, you're saying, I want you to tell me all the pixels that belong to all the individual instances of every category. So it's kind of a combination of segmentation and detection. So here, in this case, now, these two chairs being different colors would tell me that it's like, okay, I have chair number 1, here are all the pixels for chair number 1. There's also another chair, chair number 2, here are all the pixels for chair number 2. Now, instance segmentation, because now you have to be able to separate out these different instances, is again a more complicated loss than if you're just doing semantic segmentation. And in many cases, semantic segmentation is sufficient because if you have, for example, 2 sharks in the water, if they're separate from each other, it's very easy to just say, 2 different sharks. Like you can't have like disentangled sharks. Like you can't have like part of a shark and another part of a shark in different parts of the image. So sometimes there's good design choices you can make to use simpler structures of models and then simple heuristics on top of those to just get a more complicated thing. Yeah. Yeah, but actually setting that up, you can imagine in your loss is a little complicated, right? Because then you have to say like, well, okay, how many could there be? Like, do you predefine like numbers? You have to like set some fancy thing that predicts like instance values. So it just gets a little more complicated. You wouldn't even have to do it because a lot of this stuff is built into things like, for example, like YOLO. You can just do instance segmentation. But it's more complicated. There's more things the model has to learn, and sometimes you need more training data. There's also a third version of segmentation, which is called panoptic segmentation. That's a combo of instance segmentation and semantic segmentation. So there they've defined, and they mean the people who constructed the panoptic segmentation data set, defined 2 types of predictions. There are things and there are stuff. And so for things, you predict instances. So things are things like cars. For stuff, you just predict all the pixels that belong to that category. So that's things like sky or grass. Annoyingly for me, they put trees in the stuff category. So you don't get individual tree predictions because they haven't collected the training data for it. But so in that case, this is literally just the humans who constructed this data set defined what were things and what were stuff. They did this usually based on self-driving cars as like goals. But essentially all we're saying there is it is possible to do a combo of instance and semantic segmentation. You just have to design that into your model. So now we can add time. So if you're doing something like detection, now you could also imagine doing what we call tracking. So now if you have a video, the ability to not just detect all the objects, but to assign them an identity and then match that identity over time, that's what we call tracking. Tracking is interesting because the losses and the metrics for tracking can get very, very complex. So how many of you might want to do tracking? Maybe not with your, eventually, okay. So there are like 8 different types of ways to try to evaluate how good your tracker is. The reason it gets so complicated is now you're evaluating how good the boxes are for every individual frame, how good the identities are, and then you have to make decisions about how do you penalize models if they, for example, do what we call identity switching. So now you have 2 things coming in, and then you swap their identities. Now are you penalizing them? Is the tracker getting penalized for the rest of the frame? Like maybe that's not what we want to do. Maybe we only want to penalize them for the switching point. Or maybe you lose an identity at one point and then you generate a new one, but then you track it correctly for the rest of the thing. But now for all of those, it's the wrong identity. And so it gets really complicated in terms of how you think about handling all these corner cases in terms of like what happens over time. If any of you do get into the point where you're doing tracking, very happy to talk you through all the things that we've learned about tracking and tracking metrics. But the good news is a lot of trackers, a lot of like state-of-the-art tracking models, like there are really fancy ones that use 3D convolutions and incredibly computationally expensive stuff. And then a lot of stuff is pretty good if you just do frame-wise detection and then use essentially some really simple algorithms for associating those detections over time that are based on things like how much there's intersection between the 2 boxes over time. That works really well for things like this. There's a great sort of open source code for something called sort that just uses a combination of that box association and what's called optical flow. It just looks at like the way that things are moving statistically. And then there's more and more complex versions of that. The problem is where's my fish friend with all the fish? Yeah. Doesn't work so well when you have a lot of occlusions. And occlusion is another term that we'll throw around a lot, but it basically means one of your objects is hidden behind another object. So when you have a lot of occlusions, a lot of different objects, things going in and out of frame, tracking gets much harder. Also, there's a big debate on whether if you want to count things, whether it is important to do detect, track, count, or whether you want to just directly try to predict counts. And detect, track, count gives you interpretability because it's really easy to see why the model is getting the count that it's getting. But it's also a lot of different complex things to learn, and you're juggling these different metrics for the different parts of the pipeline. Maybe just directly predicting counts could be more accurate, but less interpretable. All right, so going beyond like the structure of things like detections or tracks, you can also have other types of what we call like structured prediction. So these are things that aren't just like this whole image gets a category kitchen, but this is one example of structured prediction where we're predicting the pose of the humans in the image. And so here you actually define in your ground truth these different types of key points that you're looking for, so like eyes and ears and shoulders. You define the skeleton that represents them. And then there's different mechanisms for doing this. You can do pose detection that is bottom up, and you can also do it that's top down. What that means is the bottom up version is you find all the eyes in the image, and you find all the shoulders, you find all the things. So you detect and categorize all the different stuff, and then you try to combine those into skeletons to decide which ones are likely to belong to each other. And then the top-down version is you find all the people, and then for each box that has a person in it, now you try to find the skeleton within them. Both mechanisms totally work, different algorithms for different ways to do it. And then you can get more fancy with your structured prediction. So this is, for example, the prediction of the 3D shape and structure of a human. It's actually predicting like a 3D mesh that has, it's a much, much more complicated structured prediction output. And you can imagine, essentially, as these things get more expensive, or get more computationally complex, the ground truth for them gets more expensive. So collecting ground truth for the 3D mesh pose of humans requires an incredibly expensive, like multi-camera setup. There's very few people on Earth who can actually collect this stuff at scale, whereas collecting labels for images is reasonably cheap. So there's a lot of kind of trade-offs when you're thinking about what is my goal in terms of like deciding like how to structure the problem. How do you formulate the problem as like one of these machine learning tasks where you're balancing the complexity, what labeled data you have, how expensive the labels are to get, how much data you have, and what the actual goal is. Like how much complexity do you need to be able to actually answer your problem? Cool. So I'm going to wax philosophical for a second because I think it's really interesting, and you guys can ignore me if you want. Okay, so a multilayer perceptron, which we talked about, which is a linear combination of neurons, a neuron-wise nonlinearity, a point-wise nonlinearity, and a linear combination of neurons, is mathematically provable to be able to approximate any function on Earth. So you could use a multilayer perceptron. Now, the width of that multilayer perceptron might have to be very wide. So you might have to have a lot of neurons in each of those layers, but you can use this model to learn anything. Why don't we do that? It turns out that you can, but it might be really inefficient. So multilayer perceptrons are universal. They are the universal approximator. They're simple. The theory for them is very easy to write. Right? We can actually write down a lot of really nice theory about what is going to generalize with these. They're embarrassingly parallel, so it's very, very easy to calculate these things with massive parallelization, which means they're computationally efficient. But the reason that they're inefficient is they have really weak inductive biases. So basically, like this model, this structure of architecture knows almost nothing about the data itself, right? We haven't built any hypotheses or any information into the structure of the model, so it has to learn everything from scratch. And that makes them really sample inefficient, or sometimes people will call this data hungry. You could use this, you could use a multilayer perceptron to classify species, but you would need a lot of data to get that thing to work well. And then those dense layers, those fully connected layers, like every single pixel mapping to like a million other things, they take a lot of compute. So they're not very efficient. So why do we use other architectures? So what's the intuition between using other architectures? So you can imagine that this is like all the possible mappings from X to Y. So all the possible mappings from your inputs to the outputs you want. So this is maybe like, all the things you could represent with a multilayer perceptron, right? So just imagine this is sort of like a hypothetical space of all possible models. Now, the true solution, like the true optimal that you're looking for is this green dot. We want to learn that model. And maybe we have a set of data, right? And so maybe there's a bunch of possible models that do actually fit our data. And that's almost always true, right? Like there's almost always multiple models that will fit the same type of data, particularly if you're considering all possible models on Earth. So this is the space of everything that fits the data we have. And this is the true solution. So maybe we train a machine learning model and our learned solution is over there. Maybe that's good enough, maybe it isn't, right? So what are some of the ways that we can try to improve this? So what's one way that we could try to get our learned solution to be closer to the true solution? It's philosophical. Well, we know we're going to learn a solution somewhere within all the stuff that fits the data, right? So if we could shrink the green, that would help. And the way that we can shrink the green is adding more data, because if you have more data, the number of possible models that fit the data will be smaller, right? So if you can shrink that, that sort of possible space of things that fit your data by just adding more data, that will almost by definition mean that you learn a closer solution. But there's another way that we can try to improve things as well, right? And so if you don't have more data, one thing you can do is you can try to construct a hypothesis space, right? A space of things you know about the problem that can constrain the possible solutions. And this is what a machine learning architecture choice would do. Essentially, you're defining a set of possible models that have some structure that you're going to consider. And now you have all the possible models that fit the data, plus your sort of hypothesis space that you defined based on like a type of model, a structure of model. And now you're only going to look at the intersection of the two in terms of the things that are actually possible to learn. And so architectures are another way to try to get a better solution given a set of data. Now, this hypothesis space, I don't want you guys to think like, wow, this means that I should probably do try a bunch of different architectures and train all of them and like see what happens because maybe one of them is a better fit. It turns out that a lot of the modern machine learning architectures we have gave you like the same spotlight. Like the set of what is possible to learn from a machine learning architecture for a given fixed set of data, often the differences are very small. But where the differences can be big are things like going from a multilayer perceptron to a network that includes something like convolution, or a network that includes something like attention, like a transformer does. And so I'll talk a little bit about some of the kind of ways that we build hypotheses about the world into our models and the building blocks that we've then added beyond linear layers that help us kind of constrain this space in a useful way. So you can pin down the truth either by adding more data or by using a more constrained architecture. And the less data you have, sometimes the more constraints you have to build into your system. This also, like if any of you are doing statistics, makes sense too, right? Like, well, depends on how Bayesian you feel, but you need a better prior if you don't have as much data, right? Okay, so here's a really simple version of that. If you had a 5-layer neural network that's using ReLUs as your nonlinearities, if your true solution is this green line, and your learned solution is the blue line, and then the amount of training data you have are these black dots, right? So if you only have a single training point, the learned solution you're going to have might be a really bad fit. If you have a few more training points, and you're just using sort of this multi-layer perceptron style thing, it could learn anything, you still get a really bad fit. And if you have a lot of data points, but for only one part of your solution, you might get a really good fit there, but it's going to not generalize well. And Julia will be talking a lot more about generalization later today. So the simple way that you could kind of constrain this hypothesis space, if you know that your function takes the form y equals ax plus sine bx squared, and you're just trying to learn a and b, like, well, maybe with one data point, it's still a really bad fit, but with only 5 data points, your fit is much, much better, right? Because you had an almost perfect hypothesis, like you knew exactly the form of the function. And even if you add like a lot more data, you're still really not like losing, you have much better generalization. Now, again, this is like a very nice, clean, simple version of this. And in reality, a lot of the machine learning architectures have sort of similar assumptions that they're making. And so it's not like you get a lot more from changing from one architecture to another. But the right architecture can help you generalize outside the training distribution better than not. Ideally, a good architecture is one that represents the true function and is otherwise minimal, right? So it's easier to search over gradient-based learning, easy to parallelize, fast on a GPU. All right, so let's talk about one of the most common types of architectures that we encounter when we talk about computer vision, which is convolutional neural networks. So convolution is a linear shift invariant transformation. And let me be very clear. Again, we're just talking about matrices multiplied by matrices. So here, if we define a convolutional filter, this thing, this is a matrix, right? It's ones or zeros. So let's say white is 1 and black is 0. And this filter, it's a matrix, right? And that filter defines something that we're looking for. And so what we would do is we run that filter over the image, and then you get out what we call the activation of that filter for the image. And so you kind of run it over. So say for every sort of patch, you multiply that filter with the pixels in the patch. And anything that, if you have stuff that's like similar, so here if this is dark and this is light, you're multiplying all these values together and then summing them up. And so if you have things that are very close to this, you'll get really high values. And so here, this filter, you could consider it a filter that's looking for a specific type of boundary between light and dark. And it's going to activate really high. It's going to give you a really high output value when you have something that's dark next to something that's light vertically, because that's the way this filter is constructed. And so when we run this over the image, what you get is you get these really bright white edges every time we're transitioning from dark to light. And what this assumes, this idea of convolution, is that there is local structure. So within a given region or a patch of an image, there is useful information that you might actually want to share. And in some ways, the assumption here, and it adds a lot of efficiency, is that non-local structure might be less important. So if I'm trying to figure out where the edges are in the image, if I want to figure out if there's an edge right here, I don't need to know anything about what's over there. So I can remove all of those multiplications that would take you from the far away, non-local parts of an image and really just focus on local patch-wise feature representation. So that's kind of the intuition behind it, right? And we did convolution long before we did deep neural networks, right? We used convolutions. I mean, you can use them in audio to do things like bandpass filters. I mean, it's just like a mechanism for trying to, again, process data that assumes that local structure is important. And you know, you can imagine running the same convolutional filter over many different images and you'd get the same output. And the cool thing about these convolutions is that because they're translation and shift invariant, you can run a convolutional filter over any size of image, right? Like it's not like, oh, you have to use like a specific size of image. From the simplest perspective, you can just use this convolutional filter and you could run it over anything, any input size, whatever, and you could get an output. Yeah. Yeah. So yes, and there's interesting ways that we get around that, right? So one thing is if you stack them, now you can kind of find things that are at different spatial scales. You can also explicitly use, and a lot of neural network architectures use what are called like pyramids, which is essentially like they use a few different sizes of filters and then they aggregate them in some way so that you're capturing like scale invariance. So convolutional filters are not scale invariant. They're just translation invariant. Okay, um, so basically, I'm not going to go into a lot of the details. I have some slides on it if you guys want to see them later, but I'm not going to go into a lot of the details on like how these are actually implemented. The important thing to know is that essentially, instead of constructing a linear layer, you can construct a convolutional layer, which is essentially going to, instead of doing like y equals mx plus b, you're going to learn those filters. And you can learn a bunch of different filters and run them over an image. And now your output representations are going to be the outputs of the learned filters over your input data. And you can do that a bunch of times. And it can give you this really nice kind of spatial structure. Because all the things we were talking about before, if you flatten out an image and now you do a linear if you use one of those linear layers, you don't have any information about locality, about what's close to each other. Like that stuff kind of gets lost. Whereas these convolutional filters are taking this kind of perspective of like designing something that understands that there's valuable local structure within an image. It almost by design constrains the problem so that you are now building stuff that is localizable. Cool, so 5 views on what convolutional layers do. So one thing is they're equivariant to translation. So if you took that cloudfish and you shifted it over, now you ran the convolutional layer, the convolutional features on the first one and on the second one, you would get the same convolutional output, but shifted over in the same way. So you can, they're invariant to translation, which is quite nice. You can think of them as patch processing, right? It's a way to think about capturing information with local spatial structure, which is quite useful for images, you can imagine. You can think of them as image filters. So you're designing filters that are giving you useful representations of images. You can think of them as a way to share parameters, because it turns out that now all you're learning is like maybe like a 9x9 or a 12x12 filter of weights instead of like a 512x512 matrix of weights. So, and then you're using those same weights everywhere in the image. So you're sharing the weights, and which then really reduces the computational complexity of what you need to learn. You can also think about them as a way to process variable size tensors, because you can run them on anything of any size. Now, that's true if you're running things image by image, but often because we want to do stuff batch-wise. We have to actually force all of our images to be the same size so that we can do that batch parallelization effectively. So we all often have to do stuff that way, whether we want it or not. So what happens if you stack convolutional layers? So if you have like now, maybe we had this local scale convolution, which is like we've learned this red, yellow, and green set of weights, and now we convolve that over our entire input, and we get the outputs for every single point. Now we learn a new convolutional layer. So now we've learned the blue, pink, and orange, and we're going to convolve that over all of these to get another set of weights. So you can stack these, and then you can put nonlinearities in between, just like we did with the linear layers. And essentially now what you get is now your entire convolutional neural network acts like a nonlinear convolutional filter. And so what this means is that essentially now the output for a given output value in sort of some output space will depend on this set of inputs. So before I said the words receptive field, that's a term that we use to essentially say, like, for a given feature in one of these embeddings, what were the inputs that contributed to that feature? And with convolution, it's not always the whole image, right? You actually have some more local structure or spatial structure. So what if you have color? Okay, multiple input channels. Essentially then, instead of just learning weights for, red, just like a single channel, now you have red channel, green channel, blue channel. You learn convolutional weights for each of those input values, and then you can still get a single output. So you can convolve now this like RGB convolution, and you can get a single feature output. But you can also define multi-channel outputs. So that's like, okay, maybe we have this like grayscale image, but now we're going to learn two different convolutional features. So essentially this is one filter and this is another filter. So you can learn multiple filters at the same time and get multiple outputs in parallel from a given sort of layer. And if you kind of combine that, so now you have this like filter bank output of like C filters. In general, convolutional layers tend to be multi-input, multi-output, right? So in this case, Xn is multi-input because it has red, green, and blue channels for our pixel values. And then we have this set of a bunch of C out filters, so a bunch of different filters that we're going to convolve over these three channels. And then we're going to get out a set of essentially sort of the number of outputs that output sort of feature representations, like stacked. And so you can calculate, like, based on the number of filters and like the input size and the stride length and all this stuff, you can calculate what the shape of your outputs is going to be. The point here is that with convolution, you can have multi-channel inputs and multi-channel outputs. And in most modern convolutional neural networks, you end up with both. So you have input channels and output channels. So what that actually kind of looks like, if you kind of want a visualization, like, okay, you'd have a bank of like maybe two different filters. You would take the inputs, like maybe like, red and green or something here. You would convolve them with this filter. That would give you this like red, or this like, first feature output. And then this one would take all the inputs, convolve them, and then it would give you that output. Is this making a little bit of sense? It's basically just like you can have a bunch of stuff in parallel every time. So I think this is a nice way to visualize it. So say we have our input image of this. Who knows what that is? Thank you. Green heron. You have red, green, and blue channels for your green heron. All right, so our first layer, we're going to run this through C1 different filters, right? And so your filters, you're gonna have different filters for RGB, and every single one of those filters. So for example, here, you'd have your RGB inputs with orange. Now you have RGB learned filters. So you have a different filter that's learned in this bank for each of those red, green, and blue. Now you're gonna convolve that with this, and it'll give you that feature map output, this orange one here, right? So like a single one of these sets of convolutions will give you a single feature map output. And then you do it again. So now you have all of these different channels, right? So instead of just red, green, and blue, we have a channel for every single one of those filters that we learned. Now you run them through a bunch more filters, and now you get even more feature maps. And you can imagine that this kind of stacks and stacks and stacks in these convolutional neural networks that are very deep. And so now you start getting feature maps that could actually be quite semantically meaningful. And you will see sort of some of these different channels will capture like semantically meaningful stuff like feathers or eyes or beaks. If you ever see those diagrams that are just like a bunch of boxes stacked together, like this is kind of what they're trying to show. Like how many channels, how many filter outputs, how many features you see for each of those layers. Cool. So we talked about computation in neural net. So now you have, instead of a linear layer and something like a nonlinearity, instead you might have a set of filters. So that's, all those different filters that we learn, those convolutional filters. Then maybe you do your nonlinearity. And then maybe you want to do something like pooling, which is basically just downsampling. You can just take an average of like sort of a local structure, just another simple mathematical mechanism you can use to kind of share information across all the different features. And then you could try to classify. So now in the CNN, it might look something more like this instead of having linear layers. But you can also, instead of just pooling features, you can downsample. And so here, you can reduce the amount of computation in the network by running it through all your filters, your ReLUs, and then instead of just, doing some sort of weird, like taking the maximum from a set and taking that out, you can do some form of downsampling, which is like, okay, I'm going to take a 9x9 set of all of these output features, and I'm just going to average them and get a single output. So we can do things like average pooling or max pooling. Again, just tricks that people use that help increase the computational efficiency and some of the robustness of the models. And so now the outputs might be much smaller spatially, which is computationally efficient. And then when we talk about receptive fields, I talked about this a bit. Essentially this idea that like through these different convolutions and nonlinearities, maybe you're predicting some output from each like sort of different specific space. And then, okay. So if I care about like understanding what pixels in the original image contributed to this output value right here, you can trace that back through the convolutions and find that it was like just these intermediate ones. You can also talk about the receptive field of embeddings, right? So if I want to know the receptive field of this specific intermediate layer, you can trace that back as well. And receptive field, this concept of receptive field, that's where when you talk about things like scale, that's where that can come in, right? So you could design your network to make sure that the receptive fields that you're looking at might capture everything you care about. Because if your receptive field, you're trying to predict categories, but the receptive field is so small that you're just getting like tips of wings or something, it might not be very easy to be able to predict. So you want to make sure that your receptive fields are large enough for your data that you're capturing what you actually care about. You want to have like a large enough receptive field that you can see the whole bird, right? Okay, so some popular sort of structures of these architectures. This is a really popular version, right? You have a bunch of different filters, and then you downsample, so you end up going from stuff that has really wide spatial extent to much smaller spatial extent before you actually make the classification. But you also will see architectures that are called like encoder architectures or decoder architectures. And so here, the idea is that you would learn something that would go from this bird and encode it down to some very low rank, very small representation. And then you could learn a decoder that would map from that representation back to the image. And so you might have heard things like variational autoencoder or even just like encoder-decoder generally. It's like a mechanism to try to train stuff where you want maybe this thing you think will be good for categorization, but as part of the training signal, you can actually train the model to go from that and decode. And then when you think about things like image generation, this is a mechanism to generate images, right? Because then you can change Z a little bit and decode it, and you might get a slightly different image. And the original image generators, things like the sort of simple generators would go from something like this and then decode it to an image. Mm-hmm. So pooling, I had slides for this and I took them out. Now I regret it. So pooling might just give you some robustness. So for example, say I have an edge, like that clownfish edge. Now I'm running a filter over it, and I'm getting output values. So maybe I want to make sure that like I don't really care if the edge was like at this pixel or this pixel. I just want to know that there was an edge in the general region. So then pooling can give you like some robustness to like the specific positioning of stuff, right? So if I'm gonna pull up my slide, sorry. I had a really nice slide for this that I removed, so you're getting it back. Here. Okay, let's talk about pooling. So you have your convolutional filter. So what pooling would do is essentially, this is something like, now you keeping the same size of output, but you're just saying, I want all three of these things. I'm just gonna take an average and use that as the value for this one. And I would take an average here. Honestly, a lot of pooling is like a very simple form of convolution, just like a really, really dumb one where all you're doing is taking an average. So you can do max pooling, which is like taking the maximum value. You can do average pooling, mean pooling. So why? Okay, so if you have pooling across spatial locations, you get stability with regard to small translations. So here, if you're using something like you're finding these edges and you're taking a max, now as you like shift it, you get a large response from that position, regardless of the exact position of the edge. So you get like a larger response for edginess, almost by like kind of making sure that you're not too sensitive to like the specific translation or scale or location of the pixels. So that's why you might do pooling. It does tend to add some robustness, but often what we do is, no. So then you also can do things like pool across channels. So not just pooling across pixels, but pooling across channels will tell you something like, oh, I want to find any direction of edge. So I'm just looking for edges. If I have all of these different filters that capture different directionalities of edges, and then I pool across all of those, now I'm going to get something that's very highly lit up anytime there's any sort of edge, as opposed to only some directionalities of edges, right? Okay. So then if you instead want to downsample, yeah, that's basically like, then that's like adding this additional dimension of like reducing the computation and building like almost purposeful information bottlenecks, right? You're trying to force the model to like use less weights or less sort of representations to capture the information, which is useful because it makes it more efficient and sometimes it can make it more accurate. All right. Hopeful? I should have left those in. Sam told me to take them out. He's like, no one cares about pooling. All right. So if you take an encoder and a decoder, sometimes this is really useful for doing what we call image-to-image prediction. So things like semantic segmentation. Because when you're doing semantic segmentation, you actually need a prediction for every single pixel value, right? Or at least close to. But you probably don't want something that's just fully connected layers all the way through because it'd be incredibly computationally expensive. So instead, you'll do this convolution, nonlinearity, subsample. You do that a few times so you get to something that is lower, lower spatial scale, maybe has a lot of filters. And then you do convolution, nonlinearity, upsample. And you upsample a few times. And so now you have this kind of nice, semantically meaningful intermediate representation, but you actually are able to upsample to get something that is the whole size of the image. Now, that's the simplest version, but one of the most common versions is what's called a unet, which takes that same idea of downsampling and then upsampling to do semantic segmentation, but we add in these things called skipped connections, which is essentially just you let the model choose to just take the features at that higher resolution and just directly access them later in the network. And the reason that this is helpful is it means that sometimes things like fine details around the edges of something, if you remove all that spatial extent, you lose the information you need to be accurate about the boundaries of things. Yeah. So the question is like, how much of these like the design of these different architectures was driven by intuition versus how much was driven by just pure experimentation. So there's like a running joke in the machine learning field, which is instead of doing like gradient descent, we do like graduate descent, which is basically like there's a lot of grad students and they're all trying stuff and some of it sticks. So I think it's a little bit of both. So a lot of people, if you're going to try a new architecture, you are doing it because you have some intuition about like a failure mode. So like for this one, for unet, right? They were like, we're not getting good accuracy around the boundaries. And part of the reason is that like, how the heck would this model know about the edges of the feathers if we've downsampled it to be much, much smaller? So then the intuition was like, okay, well, what's a way that we can let it sort of try to keep that information bottleneck and like that semantic kind of forcing, but then let it keep the detailed textual information. And so then they added in these skipped connections. But there were so many different things kind of like this that were somewhat similar. And some of it, honestly, it's like, it's not even that it's necessarily the best, like they're all really similar. And one of them just kind of gets lucky and takes off. Sometimes it's like they had a better code base, more people could use it, you know? So I think it's a little bit of both. And this idea of a skipped connection is not only valuable for semantic segmentation, though I guess I still have this segmentation output. So one of the models that almost everyone uses that is incredibly robust and super easy to use is a model called a resnet. And the thing that a resnet does is it adds skipped connections into a convolutional neural network. So you have these different blocks of, you know, your standard convolutional neural network, but you add these skipped connections that basically you can either, your model can choose how much information it wants to route through this function, or it can literally just choose to skip it and send the features directly. One interesting way to think about this intuitively is it almost lets the network choose its own depth, right? Because the network can choose to run stuff through, maybe it's like the optimal depth for this problem is 5 layers. So the model could choose to run it through 5 layers or 4, and then skip the rest of them. Right? So it's a way to almost like build explicit flexibility, let the model learn a little bit more about what is the optimal structure. That's like one form of intuition about why these skip connections add so much value. But they do increase the robustness a lot. And these models are very easy to train. So most of you, if you're doing classification, will have you start with a resnet because they're very robust to hyperparameters. So it's like you don't have a ton of sensitivity to the specific parameters you choose, which is really nice. Like you can choose a set of like close to like the hyperparameters a lot of people start with, which kind of like learned by graduate gradient descent. And then you might get a little bit of difference in your performance, but it's not going to be huge. Versus like sometimes things like transformers can be really accurate, but they can be incredibly sensitive to hyperparameters, so they can be much what we call harder to train. You have to train a lot more models to get one that works. Yeah, so skipped connections are a nice idea. Attention actually also has a mechanism for skipped connections. Yeah, so this residual connection is basically just like you learn a function of x in, and then you add x in back to it. Or you can change the dimensionality by adding sort of some weight matrix that you multiply it by. And then, you know, like we were saying before, structured outputs aren't just segmentation. You might have something like a pose or a box. And so these are always some combination of different loss terms that will give you things like regression or classification losses to output these multiple things. And, you know, we're just showing a very simple network that's just like going straight through. But maybe if you want to do detection and pose, you might actually have what we call multiple heads, call them heads, at the end of the network. So instead of just at this last point going to just one thing, you would have it go to one and another, and one of them's job is to do classification, and one of them's job is to do the boxes, and one of them's job is to do the pose. And then you're kind of balancing the loss across all 3 of them. You can also do convolutions in time. So if you imagine this is a one-dimensional time series, you can convolve in time as well. And so this is like one way to try to start modeling temporal dimensions. And then if you imagine something like a video over time, you can also do 3D convolutions, which is basically like you're running a 3D convolutional filter through this like time cube. And then you get sort of a representation that captures not just local structure, but time. 3D convolutions are really expensive. That's a lot of multiplication, right? And there's a lot of choices you have to make about like how much of a time window, how big do you want the filters to be? And so there are a lot of architectures that use 3D convolution for modeling time and video, but increasingly people are moving to kind of clever ways to try to reduce the computational cost of these. So like one really common thing they do is there's a model that's called slow fast, where there's an expensive thing that runs every like second. It's like big, lots of computation. And then they use really, really downsampled images that they run at much faster speeds. So like you're basically running images through the model like at really low spatial resolution every single time step. And then you use a much bigger spatial resolution model like every X time steps. And then you combine those two things. It's basically there, the idea is like, all right, the difference between one image and the next is often small. You want to be able to have something that's like picking up subtle differences between frames, but it's really expensive to run a massive 3D CNN at high resolution over everything. Okay. How you guys doing? Good? All right, we're almost at time. Do you guys want to hear about transformers? Okay. I'm going to cut into lunch a little bit. Is that okay? We have a 2-hour lunch, so all right. So transformers in the last couple of years have started to be used for almost everything. They were originally designed from the perspective of text modeling, and transformers tried to basically combine the intuition about like local scale features, but they also introduced this this dimension of non-local information. So if you imagine if you're trying to, let's say, like translate a paragraph, and you're thinking about text as a sequence, sometimes when you get to the end of a sentence, it's really important to know something about what happened at the beginning of the sentence. So just convolution is sort of insufficient. You lose that like non-local attention, and especially as your what you call your context window gets bigger, so the sort of amount of text that you're looking at. Now, you know, ChatGPT can look at entire books at a time. The context windows are massive, and it does that through a lot of GPUs, but it's important to have that context from earlier in the book to be able to like make intuitive predictions. And it turns out that there's also good justification for non-local attention in images. So, you know, yeah, like local scale features are important, but maybe if you're trying to predict the behavior of an animal and you have an prey animal that's over here and it's just standing still, but there's a predator on the other side of the image, it's more likely that the behavior you would predict would be contextualized by that predator, for example. All right, so the first idea when we're moving to, there's like 3 big ideas I'm going to introduce the concept of transformers. The first idea is tokens. So we're introducing this new data structure. A token is transformer lingo for a vector of neurons. So graph neural networks also operate over tokens. We call them node attributes or feature descriptors. We're going to go with tokens. The connotation is that a token is an encapsulated bundle of information. And so with transformers, we operate over tokens instead of over individual neurons. And so here it's like, here's like an array of neurons, right? So this is like what we've been talking about so far, where every individual little thing is its own entity. Transformers move to more kind of like patches or tokens that are representing sort of like local structure in some way. So instead of an array of neurons, you basically have an array of what we call tokens, or like an array of like essentially small little feature representations that are representing patches. And so, for example, in the text space, it's kind of easier to introduce this stuff when you think about text. This might be a representation of each word in a sentence. So now there's this idea that this is captured. When you talk about vision transformers, each of these is a representation of a patch of the image that's maybe being slid across the image. So now you're kind of running this feature through something, and now you have this little token. It's like a small vector of representation. And now you can have matrices of neurons. You can also have matrices of these tokens. You can also have sets of neurons and sets of tokens. Essentially, we're just moving from like single numbers to little vectors everywhere. So if you're talking about tokenizing your input data, now you have your input. You basically take all of these different patches, and then you generate a token representation for each patch. And this might be something like a linear projection, right? Like it could just be like a linear layer that you learn that generates that token for every patch. And the important part is that that linear projection is going to be shared. So you're going to use the same filter for every patch. Now, when you're operating over neurons, you represent the input as this array of scalar valued measurements like pixels. When you're operating over tokens, you represent the input as arrays of vector valued measurements. So now the important point is you can tokenize anything. So you can have this idea of like tokens for almost any type of thing, right? You can have tokens for images, you can have tokens for text, you can have tokens for audio that are like sort of snippets of sound. And essentially what you're just saying is like, here's a bunch of little representations of little bits of my input. So now say you have some token, then that'll kind of have some sort of token code that's represented. You can do linear combinations of tokens, just like you can do linear combinations of neurons, right? So now here you're just doing a linear combination of those little features, feature representations. And you can do token-wise nonlinearities. So instead of taking a ReLU over each neuron, you would take some nonlinear function over the feature. And typically that function is a multilayer perceptron. So you basically, instead of having a pointwise nonlinearity, you actually take those features and you run them through a little tiny neural network that has a pointwise nonlinearity in it. All right. So it could be considered to equivalent to a CNN, a convolutional neural network, if you use 1-by-1 kernels. So that just basically means like running over the token sequence, but like your kernel size is 1. So it's like convolution, but it's kind of like a multilayer perceptron. This is like not super important. But so here, right, so we have like now we have this like non-linearity over our feature, and then we run that like feature-wise or token-wise across the model. So you do this token-wise nonlinearity, but it's not node-wise nonlinearity. All right. So now we had this idea of like a neural net where you have linear combinations of neurons, neuron-wise nonlinearities. We can also now introduce the concept of like a token net. And this is basically what a transformer is you're doing things like linear combinations and token-wise nonlinearities across these little patch-wise features. Okay. And like a graph neural network, often you might have the same idea, right? Like a lot of when people operate on graphs, they're also using this concept of tokens. So this idea of tokens was really introduced with graph neural networks and then got kind of cannibalized into NLP to turn into what became modern attention. If you want to think about this, a view of this from the graph perspective, so sets are like graphs without edges, and you can build a complete graph over any set. And so a transformer is basically like now all of these graphs, like all of these nodes, those are little tokens. And then we're going to build a complete graph over the set of tokens, which basically says like any token can share information with any other token. This is where the nonlinearity comes in, because like now you have all of these little patches that have all their little feature representations. And now instead of just looking locally, we're going to look globally. We say, okay, for this patch, for my next like representation of that patch, I can aggregate information from any other patch in the entire image. So we've essentially constructed a complete dense graph over all the little token representations of the inputs. Okay. So that's tokens. So basically now we're just moving to a space where we're operating on these little tiny feature embeddings of things instead of operating on individual neurons. So the second big idea is attention. And this is essentially the mechanism with which we share that information globally. So a limitation of CNNs, if we want to say something like how many birds are in this image, that's maybe not so hard, but if we want to say, is the top right bird the same species as the bottom left bird, that's where those receptive fields can start to become tricky, right? So CNNs are built around this idea of locality, and they're not well suited to modeling long distance relationships. So what attention does is now it says, if I want to say how many birds are in this image, and now I have all the regions that have birds, which would be kind of represented as tokens, or I want to say something like, is the top right bird the same species as the bottom left bird? I kind of have access to whatever information I would need to answer those kinds of questions. Or, you know, maybe what's the color of the sky? Well, now their useful information is going to be different tokens, but I still have access to all the tokens. So now what the model is learning is what is useful for a given predictive task, right? So there's different ways to think about aggregating information over space. So if we look at these helmeted guinea fowl, if you have convolution without overlap, essentially there, like I'm saying, like I'm gonna make a decision about this patch independently of any of the other patches. I can build convolution with overlap. So now I'm like, okay, my receptive field is gonna be a couple patches. So I'm gonna make a decision about this patch, but I'll incorporate information from this patch too. Or I'm gonna make a decision about this patch, I'll incorporate information from these 3 patches. So that gives you this local scale stuff. you can think about these convolutional pyramids. So that's where you can kind of increase the scale, where you say, okay, I want to make decisions, and I'm going to make sure that we're aggregating in a way that means that my final decision gets information from everything. Or we can use fully connected layers, which are like those linear layers we learned right at the beginning, where now for any decision I make about any of these kind of local patches, I'm going to have access to all the information across all the patches. And this is essentially what kind of is, but it's expensive. So what attention does is, instead of that fully connected layer where you're learning these weights that you're going to use for all of these different combinations of inputs to outputs, instead we're going to use this, what we call this attention mechanism, which tries to let the model learn what information is important and how to use that information. All right. So digging into attention a little bit. If you have a fully connected layer versus an attention layer, all of W are what we call free parameters, right? So you're learning all those parameters independently. Whereas with attention, that function is going to be a function of the input data. So the data itself, like the input image that you use, tells us something about which tokens are most important. So you assign high weight in your weighted sum. Here you're taking a weighted sum, but you learn that weighted sum over all the data. Here you're taking a weighted sum, but that input data actually conditions the weighted sum. So you're taking a weighted sum that is most valuable for a given input. Okay. So if I want to say something like, what color is the bird's head? Here. All right. So those are probably the 3 patches that are most important or most useful for answering that question in this particular context. And then maybe I could say some representation, which is basically like finding the pixels that correspond to the head and taking the average for each of those, which might be happening within those kind of representations that we're learning. And then maybe I take an average of those, and I can say, okay, the color of the bird's head is blue. So this is really just sort of showing, like, if you can kind of condition on the input. In this case, conditioning on the input is conditioning on some sort of question we want to ask, but maybe it's like conditioning on the category we want to predict for the species. The idea is that your model can learn what the most useful parts of the image are to make decisions. Talking about what color the vegetation is, different patches are going to be useful, right? So now you're going to maybe say something about, okay, yeah, like the vegetation is green. So notation reminder, the token is T, this like token code vector, this little like vector, that's like the representation, and we're going to use T point Z to represent that. Yeah. So the so this is like the input of that little like the little tiny neural network that you're going to use to get a representation for each patch, and this is like the output. I'll get there. The same. So it's not different in terms of, it's not even necessarily different in terms of your loss. It's not different in terms of your data. It's different. It's just like, you can think of these attention blocks as like a drop-in swap for what you might use a convolution for previously. So it's not any different in terms of the actual data. The difference is like the mathematical mechanism or the building block that you use in the model. And I'll get into it a little bit more. I know this is like, it's a bit advanced, but transformers get used so much now that I think it's like, it's good to have a sense of what's going on. Okay, so this is now, what we're going to talk about is how you do it. How you get your model to learn what's useful instead of just using like fixed convolutional filter weights. Okay, so we're going to introduce the concept of what we call query, key, value, attention. So what any of those little attention blocks inside a transformer is going to be doing this. All right, so maybe our question is, what color is the bird's head? Our input data is these patches and these little representations for each patch. So we can assume right now that we have all of these different input patches, and for each input patch, we've run them through a little multi-layer perceptron, so maybe like a linear layer, a non-linearity, another linear layer, and we get a little representation for each patch. So that's what this is. So now our input data to our attention layer are these little representation vectors for every patch. You have one of them for every single patch in the image. So what we do is the query, in this case, is this question, what color is the bird's head? And we have some representation of this question as well, right? So it might be good to make this like just images. So another version of like a query, like the query doesn't have to be a text question. The query can be another patch, right? Like you can say, the query could be this, and my kind of query that I'm posing could be, find me all the things that are similar to this, right? And then you have some little representational embedding. All right, so now you have this query, this representational little patch, and you duplicate it 4 times. So you have the same query for every single part of this attention mechanism. And then you generate what we call a key. So this is a function that's learned. It's shared weights across all of these. They're usually just a linear projection. So you have this vector, and you're going to basically generate like 4 of them here. And if sometimes there's what we call a query projection, which is just like a single linear layer that would project that input to a new space. And so you have one projection that's going to make these yellow things, and then you take these little black guys and you use your key projection to generate these pink things. Those projections are linear layers, and the parameters for those linear layers are learned. But they're the same projections for every single patch. Now, what you can think about is like what you're learning for this combination of query and key is like the model is learning how to, the model's learning to project 2 different types of information into a space where you can now ask what is important. So the queries and keys are telling you what is important. So now I'll get a score for each of these patches by just taking vector multiplication between like the keys and the queries for each patch. I'll get a score for how important that patch is to this query, right? So that's basically telling me these little scores here are saying like, for a given query, how important are each of these patches? How valuable are each of these patches? And so that those learned projections are just telling you how to determine what's important. Then you have a third projection, which is that value projection. So now you take these patches and you learn a different thing, a different projection. And this is like, how am I going to use that information projection? So now these, you have now like a new potentially like output representation from each patch. And then the way the attention actually works is you use the scores based on how important is the information to take a weighted sum over the values. It sounds really complicated, but it's actually kind of not that complicated. So essentially what you're learning is 3 small linear layers. One of them operates only on the query. One of them operates on every patch to generate the keys, which tell you basically what's the similarity between this query and this key. And then the last one basically tells you how do you want to use the similarity to now send it forward to the next layer of the network. So then you do that linear combination with those weights that are determined by the value, the kind of like key query component and the values that are going out. Then you take a softmax over it, just like we did before, which is like essentially forcing it to sum to 1. And now your output is that. So now it's like, all right, now you can imagine, you can have, this is an attention block. All of this stuff is like a single attention block. Now you can have multiple attention blocks in parallel, where the only things you're learning for those attention blocks are these little projection functions, these little dotted lines, and they're shared for every single patch. So the computation itself can be really lightweight, right? Like it could be like, if your patches, if your little patch representations are like 128 dimensions, like you can learn these projections to just like 128 to 128, which is really small versus like very large scale. So self-attention is often what's happening within vision transformers, which is kind of what I was talking about before, where instead of having like a question you might ask, you're gonna have like, here is the query, and now the query is a given patch of the image. And then now you're going to find all of the stuff in the image that is like most relevant to that. So it might find, for example, the other heads, and then you're gonna do this, this combined sum. Now, it's going to be doing this. It's not only going to highlight these. The reason these are getting highlighted is because their scores are going to be really high. All the other stuff will have a score too, but the score might be really low in terms of that factor multiplication between the keys and the values, the keys and the queries. Okay, so that's it. That's how transformers work. You basically take those attention blocks and then you stack a bunch of them in series, and then you stack a bunch of those in parallel, and then you just have a transformer. That's basically all it is. And so you're learning all these little linear projections that are telling you what information is important and how to use that information. That's all it is. And it's pretty cool. So this is these are videos, and then this is attention maps in a trained transformer. So this is showing you what the scores were for those patches in a transformer that was trained to do, I don't know, something. But you can tell that like the model's deciding that like some of these kind of things are, you know, and this is, it's the reason this is cool, this is kind of nerdy, but like all of these are videos where there's an object moving and the background is moving, and it's doing an amazing job of isolating the object movement from the background movement. Cool. Okay, so now you can do that. Yeah, go ahead. No. So the question is, what's the training data that would have gone into this example? And I'm pretty sure that this is actually, this is Dino, so it's supervised with class labels. And actually a lot of it, but then they do a lot of like self-training too. So a lot of kind of like, uh, there's like mechanisms to like try to train models to pick up on what's valuable without any labels, like self-supervised learning. And so if you want to read the Dino paper, there's like specifics around like how they trained this model, but they use some like creative tricks to try to get more out of the training data than just like the category label that they have. Yeah. Mm-hmm. So the question was, in this example, like if you were saying like, oh, how does the model like know? Did someone have to label like, oh, there are like these three blue heads in the picture? No. So the point is that the model is just learning what's important. And so here, like if the output, like if the output is like, it depends on like what the task is. If the task was like, what is the head, what is the average color of the bird head, then your label would need to be for this image blue. If the task is what species is are the birds in the image, right? Then like this still might be the most useful information because helmeted guinea fowl have this very specifically blue feature. So it's just like another way for the model to learn like, you know, what's the important information. So one way I like to think about like where this attention stuff can be quite valuable is like, say you have a model that's trying to predict helmeted guinea fowl. So there's a couple of like important features, right? There's like the little helmet, there's the blue face, and then there's like the big body with the polka dots. There are other birds that have kind of polka dot bodies, maybe not exactly like this, but the blue face is pretty iconic. So if you had the blue face in the image, that's a really useful feature. But maybe you got a picture of the bird where the blue face wasn't there. So now the model can still then say, oh, okay, well, this is now the most important stuff. So it kind of like lets the model focus on the features that are available to it for any given image. Or it's just learned to relate these two different textures to helmeted guinea fowl. I don't know if it's like learned anything about the structure of a body. Yeah. And of course, like we wanna be careful that we're not anthropomorphizing too much, right? Like these models are they're just statistics, fancy statistics. Yeah. So for the videos, um, I'm pretty sure. So Dino is like one of these like very nice feature extractors. I think this is done frame-wise. I don't think they're doing videos, and I think that the frame-wise prediction is just the category. if I remember correctly, but I'm nervous that I'm forgetting exactly like the details. So we can go back and read the paper. I'll get back to you guys. But no, they definitely didn't give it any like explicit other types of labels. Like it wasn't like, but also like this idea of like this attention map, like CNNs do this too. I talked about the like activation maps. Like, so a CNN, it's not like attention is the only thing that like kind of focuses. Like if you take a given image and you run it through a convolutional neural network, you can do, there's a certain mechanism you can use to try to like propagate back through the network, like what sort of the highest weights were back to the original input image. And you see similar stuff. Like it tends to focus on like faces and like, yeah, different like identifiable parts of things. So it's not like this idea of like, oh, it's paying attention to stuff is unique to attention. But attention does it very explicitly. Right? Cool. So when you're talking about like this quote unquote self-attention, where I was like, oh, okay, you can take one of the patches and then use that as the query. What's actually often happening in vision transformers is you use every single patch as the query, and then you have every single patch as a key, and then you do this basically combinatorial like, you know, n choose n of like, okay, now I'm gonna, but you use the same weights for the projections, but now you're sort of aggregating that information from all those input patches, incorporating information from all the other patches in the image when you're then like sending information to the next layer. So essentially, you can think of this as a Graham matrix, which is a similarity matrix over tokens. So basically your outputs is basically like how similar is each of these tokens to all the other tokens in that projected space we've learned of like how to compare them. All right. No, I don't want to do this. Yeah, so a simplified version of a transformer. So this is like the attention is all you need, or the vision transformer paper. You have your input image, you break it up into patches, you run each of these through like a little tiny like neural net. Now, for each of these, we project to a key, a query, and a value, and then we do attention across all of those to all of those. And then we do it again. We run each of those little output features for each patch through another little tiny neural net, and then we do this projection to keys, queries, values, use each patch as a key, use each patch as a query, you do it like combinatorially across all of them, so you're sharing information across all the patches to all the other patches. And then you send the information forward based on relevance, like patch-wise. Yeah, and that's what a transformer looks like. And inside that attention thing, you're doing this kind of like weighted sum over relevant patches for every single patch. All right. So if you kind of translate this, it's almost like an MLP on tokens, right? Because you're doing this like self-attention instead of a linear layer, but essentially you're letting everything communicate to everything, which is kind of like a densely connected linear layer. All right, and don't care about this, sorry. Okay, the last important bit, and then we're gonna go eat lunch, is this idea of a positional encoding. So currently, we basically had a bunch of patches, we like threw them in a bag, and we let every patch talk to every other patch equally, and we lost all context about how close together the patches are. So the last little thing is that if you want the model to know something about how the patches relate to each other spatially, you can add what we call a positional encoding, which is just like another little bit of information you add to each of those little patch features, and that just tells you something about where they're located relative to each other. And usually, so now, you know, for every sort of signal, you get this position. And so that if it's a sentence, it tells you which position in the sentence you are. If it's an image, it might be a 2D positional encoding that tells you where you are in X and Y. And so from an image perspective, you can construct these positional encodings based on the coordinates, right? So you have like X coordinates are going to be like lighter at the top, darker at the bottom. Y coordinates would be like, you know, lighter to darker or whatever. But now you have this basically like positional encoding of the pixel locations of a given patch. And so you can actually apply convolutional neural networks per pixel to map from a coordinate to a color. So you can actually learn to map from positional encodings to images, which is kind of interesting. What we often do is we build these positional encodings using Fourier basis, which essentially is just like, it gives you some scale and variance to the positional encoding. So you take that X and that Y, and then you run them through a bunch of different sinusoids with different periods, and then you combine that to build your positional encoding. You guys don't have to do this. Like, this is all implemented already inside transformer architectures. But the important point here is just to note that like the last bit of missing information that you don't lose with convolution, but you do lose with these transformers is like where things are relative to each other. And so you just build these encodings that tell you exactly how they're relatively positioned. And then that's like the last bit of information. And there's some really cool work if you're trying to build sort of models of the Earth, for example, or models that give you something about like some representation of space on a planet that adapt these Fourier bases for positional encoding to handle the fact that planets are round. So there's like some cool work recently if you're doing like geospatial machine learning that actually talks about representing space and time on a planet. Maybe I'll show you guys a cool paper next week in our reading group exercise. I'm going to try to teach you guys how to do lit review on machine learning papers that talks specifically about learning these like geospatial encodings or these geospatial representations that then you can use modularly with image classification. So then it's something like, all right, what is this image? Like, what bird is this? But now you get to say, what bird is this, given that I saw it here at this time and place. But that's just another like encoding of information. Yeah. Yeah. So you're asking like with these positional encodings, like how is it kind of capturing relative position? So essentially, the simple version, which is just like you just use the X and the Y positions as your positional encoding, then like, all right, so now you have like this feature representation of the patch, and then you also have like maybe the center pixel location of the patch that you just append to the end. And so now if you have one token that's here, and now I have a token to the patch next to it, so now the Y positions are going to be identical. So like in those features, when we're talking about similarity, they're identical. And the X positions are going to be really close together. So now essentially it's saying like there's more similarity between things that are close together in the embedding space. Yeah, so that's the thing. We're telling it that we're telling it the information, but then the projection will sort of learn how useful or not useful that information is. So instead of us, we're not explicitly saying this has to be similar. We're saying like, here's the information. If it's useful to you, you can use it. Yeah. And it depends actually a bit on the patch size, right? And like the data you have, like, and those boundary layers, like what all that looks like, how useful those positional encodings are. It's interesting, you can actually look for different stuff. You can start digging into like the actual weights of some of those projection layers, and like sometimes they'll just learn to ignore the positional encoding. It's just like they decide like the model doesn't really, it's not useful information, and it just, the weights from that in the projection are always 0. So sometimes the model just ignores it. Sometimes it's super useful information. So like for like something like satellite imagery, like the fact that it's ocean here makes this much more likely to be ocean if it looks similar, right? Okay, cool. That's it. Oh, this was just me saying like, oh, you can also do this for the planet, which is cool. Okay, we did it. Good job, guys. I know that was a ton of information, and there's also so many other things I could have talked about, but pretty good for like an overview of all of computer vision in 2 hours, 2.5 hours. Let's go eat some food. And I'm here, and all the other instructors are here if you have any questions about any of this, and you should also have the slides and everything, and we'll send the recordings out if you want to re-listen to any parts of it. All right, good job, guys.